Okay, so today I am going to discuss on quotient space. It is a very abstract topic of linear algebra, and we will see that how equivalence relation, the notion of equivalence relation will help us in understanding this quotient space. However, as this one is a very abstract one, so instead of starting from an abstract idea, I would like to start with a very easy to visualize idea, and then I would like to means generalize it and also include all those abstraction in our discussion, right? So before we start, we have to understand a very simple thing, that is the parallel translation of a vector space. So obviously it sounds odd, but you can understand. First of all, if you have already heard a few of my videos, you will see that while I discuss linear uh, space, what I give you an idea that instead the means the trivial space, also known as null space, having only one element 0, or all other linear spaces or linear subspaces, because linear subspaces are also a kind of linear space by their own means composition. So what is needed, that is very simple thing, that is what I was trying to give you an idea, that if we take a three-dimensional space, although in this two-dimensional screen I can only draw, means only give you a visualization of at max three-dimensional case, not even the four-dimensional we could visualize. So in three-dimensional space, what you can have, your space, if this side all these are infinite, your space must be so if you consider existence of any means three-dimensional space, like you can visualize it in Cartesian coordinate as infinitely large, like what to say, infinite large, just a minute, infinitely large cube. Why it need to be a cube only, not any other means solid structure of three-dimensional shape in Cartesian coordinate? Because it is obliged to maintain symmetry in all direction, in all axes. And why it is this symmetry is necessary for us? Because until unless it is symmetric, you cannot get the additive inverse, right? Suppose, let me give you one idea. Suppose, obviously, if we consider a finite cube here, okay, just let me draw it, then I'll get back. So although it's a horrible drawing, but you can understand the meaning of this. Say the center of this cube is placed at the origin of this coordinate system, and you can see that any position here will have an additive inverse. However, in order to ensure the closure for addition, what you need to do, you need to ensure that the cube must be infinitely large. And obviously when you try to reduce this cube, means it is I'm talking about R3, when we will try to reduce it to R2, you can find it out like R2 must be the total two-dimensional plane, right? And also what we can have here, is that so let get back to our previous discussion. Let us, for sake of simplicity, let us consider R2. So R2 is total this space, right? This is our R2, the entire space. Now you think that in R2, let us consider a subspace of R2. Obviously, when R2 we are talking about, R can be a subspace of R2 by its own composition over the field R, but that is R is the real line. But can we take any other line like this? Let this line be capital U, and our V, the vector space, is R2, and I am claiming that this U is a subspace of V, a proper subspace of V, and U forms a linear vector space over the field F is equal to R. If you want to validate my statement, you can try to see or check whether this line corroborate with the 10 axioms. Now, what is our objective? The first statement with which I started today's lecture was a parallel translation of vector space. So in case it is a plane, it is a parallel shift of a plane. In case it is a line, we are talking about a parallel shift. Now here let us consider a vector small a. Let me select a bright color so you can understand it. So this is our small a, right? Now if I ask you to obtain a plus u, what would be the nature of a plus u? A line so if you consider an unit vector of this line, say this be the unit vector or basis of this space. Now that unit vector on this line, this will be here. However, what we can show you that we can find out another vector also, B. What is B? This one was A, this one is B. However, it results in that B plus U is the same subspace as it was. This white line is the original subspace. Let me write original subspace. Then this A plus U and B plus U both are generated by means of parallel translation, And obviously if you add this B with this blue line, this indicates a unit vector in that space capital U. If you just capital U, if you just add it, then what you will get, you can add it and you will get a vector here at B plus U will be here. Now the question that obviously that will shift your B plus U here. Now the question that may comes in your mind, but before that I go to that question, let me tell you one thing. It is very interesting to note that A plus U is equal to B plus U. However, A is not equal to B. Then obviously you can ask me a question that said, are you going to make a claim that we can add any arbitrary vector and still will get the same line as it was for A plus U? Obviously not. The answer is obviously not. Suppose we have a vector like this. Let me have a third vector. What is happening here? Say, sorry, let me have a third vector. Here it is C. So how this C will shift your this one? This C will shift this A plus U here, or sorry, C plus U will be here. Obviously C plus U is not the same line as you are having. So obviously for some vector we can have A plus U is equal to B plus U, while A is not equal to B, but not for all the vector. So we must investigate the condition that which one will ensure that even if we add two different vector with a space capital U, the translation of these vectors by the space will remain same. However, before I go to that, let me tell you some terminologies. Now how to, first of all, before going to the notion, let me write the expression. This is like pure geometry and pictorial representation, you are okay with that. But how you can write it for in set theoretic notation, we can write it like A plus U is it's defined as all the set that contains all A plus U such that small u belongs to capital U and this belongs to V for all A belongs to V, right? Similarly, you can write another vector for another vector, like for all A belongs to V means it already implies some other B belongs to V will also satisfy this, that B plus U is equal to mind it, this small u is an element, this one is an element, while this capital U is the space, right? And this again belongs to V. In our example, U is a line and V is R2. Now here one thing it's very clear for us that if we proceed in this way, okay, one more important term I forgot to write. Some people call this a plus u as the translation uh, as the, let me erase it. Some people call it this a plus u as the translation of capital U by A. Some people call it affine subspace of U. Now let us discuss one very important topic, that what we discussed from that geometry also, like for some vectors belongs to V, the mother means the original space, what you can get that A plus capital U is equal to B plus capital U, both the subspace are same and both of them are belongs to V. However, for some other vector C belongs to capital V, you can see that C plus capital U, in other way affine subspace of U by C doesn't belong to, or means is not parallel to the previous line A plus U or B plus U, or they are not same, like A plus U is not is equal to C plus U. However, A plus U is equal to B plus U. And most interesting things here to note is that A is not equal to B. So how we can prove that, what is the condition that needs to be fulfilled when we have to write this kind of statement, or we can claim that A plus U is equal to B plus U even when my take on this particular issue is that here this B minus A, obviously B and A are the two vectors of capital V, and V is a space over R. So obviously you can see that you can get -1, and B and A you can have that B minus A belongs to V. But what I would like to claim that this is possible only when B minus A is not only belongs to V, but in addition B minus A must belongs to capital U. So what we need to prove that we have to prove it, like if B minus A belongs to U, then A plus U will imply B plus U. Let me from the geometry, let me just try to explain you. See here, if you try to figure out the B minus A vector, how can you find out B minus A vector? Obviously it's very simple. You take here, it is your what? It is your minus A, and then you just go by your parallel law of addition, and you will see that this will result to something B minus A. Let me select a different color for better, you will see that this vector b minus a will also lie on the line denoted by capital U. However, we need to prove it that so basically what is my claim, that b minus a must belongs to U. In that case only so in order to prove it, what is need to be done, let us assume this is U. Let us assume this. Now, if this is the case, then what you can write? Let us start from A plus, let us start from B plus capital U. Here all are U, right? So let us start from B plus capital U. Mind it, this is a space, not an element. However, this B plus capital U, you can write it like here as B, A, U all are element, means B, A, all these are means elements or rather vectors of vector space. This one is a vector space and they are the elements of vector space. So we can assume that addition is associative. So you can put bracket or means change the like order of bracketing and you will get this. This is a vector space. Now, however, this B minus A plus U, you can write this whole thing belongs to capital U. So as I am adding this B minus A plus capital U, obviously this will also belong to capital U. Now if you have any doubt, think about that this in order to ensure the closure of addition, like B minus A, adding one B minus A with U while B minus A was previously an element of U, is the resultant, whatever you will get is no way will again be an element of capital U, because your vector space by virtue of its composition is obliged to ensure the closure of addition. So if you add one element with your vector space, then obviously that will still be the same space. So it will give you A plus capital U. That means B plus U belongs to the set B plus U, or the space B plus U is contained in the set denoted by A plus U. Similarly, if you start from the reverse way, you can show that A plus U contained in the set B plus U, they together imply that this whole thing is like A plus U is equal to B plus U, right? Now we are ready to define. So now we are ready to define a few technical terms, or rather we are ready to digest a few technical terms. So first one of them is the definition of quotient. That is nothing but the line that is plus capital U which is parallel to the original line capital U is a coset of the element A belongs to V, and similarly B plus U is a coset for B belongs to V, right? So here I would like to mention one important observation, that two cosets are either disjoint or identical. And if these cosets are distinct, they form partitions of the original space or original set V. Another important point, let A B belongs to V and in addition they also belong to a subspace W that is a proper subspace of the original space V, and W W and U are disjoint, then obviously what is the smallest set that will contain W and U? Obviously that is W plus U is the smallest set, that contains W and U both. Now if we can see that W and U are non-trivial and their intersection is means they are totally disjoint. Only one common point you will find common in them. Which one? A disjoint, actually they are not uh, disjoint. Better to say that U intersection is trivial. Now it makes sense. Disjoint means there is no element in common. However, their intersection, if I say it is trivial, then it indicates that as I have already mentioned, W and U are both subspace of V, and you must understand that if you want subspace, subspace is a vector space by its own nature, means by virtue of its own composition, subspace is also a vector space. So you need an additive identity, and for both the space, as they are the subspace of original space V, so you cannot have two different definitions of scalar vector addition and scalar multiplication for W and your U. So it is obvious that both of them have to share the same additive identity, which is 0. So I cannot say it will be incorrect to claim that W and U are disjoint. Rather, W and U are intersection is trivial. Then W plus U is the smallest subset that contains W and U. Okay. Now, if that just a minute, let me check whether it is recording. Oh, it's recording. So what would happen if they are if their intersection W and U are intersection is a trivial vector, then we can represent any other vector of V if let me write it clearly that if W and U are such that this V can be expressed as W and U, then we can say that V is the direct sum of U and W. It is like V is equal to U plus W. It is defined as the set which contains all the U plus W right? So it is the basic idea is that you can say V is a direct sum of the two subspaces if V is equal to U plus W and can you recall the this particular symbol of direct sum? Uh, can you recall your digital electronics class where we use an operation is like XOR? What was that XOR? How to write XOR? Think about it. What was that symbol you use for XOR? And then you will find that everything means this you can relate anyway. So and in addition, what we can write that W is algebraic algebraic complement. Please remember this term because in future we will be using all these terms. In V, and they together, this pair Q comma W is known as complementary pair. Right? It is a complementary pair. Now, with this, let us try to understand something that is more interesting. Like we have defined the direct sum. Now, let us understand another few definitions. Of so we have already studied that what is the means what condition must be satisfied in order to ensure that we add two different vectors with subspace and the resultant space or remains same. We studied it in terms of line, and even in R3 you can visualize. Previous example was in R2. In R3 you can visualize like you can have planes, right? Two planes you can have, like you consider you are in R3. R3 is just like your room, and now if you consider the floor is R2. One floor you take, it is R2, and if you add any two vectors and after adding them, if you see that this resultant of this addition for both the cases are a new floor which is means the same floor for both the case, then obviously you will find the vector that you add with the floor space, the difference between these two vectors also an element of this floor subspace, right? Means floor means I am talking about a two-dimensional plane R2, right? So this is sometimes denoted by a few people write it like but it is preferable that you follow this one. And now we can prove that this is exactly an equivalence relation. Can you prove it? Think about it, how we can prove that this is an equivalence relation. What makes our relation equivalent? Like if we claim that B minus A has to be a member of the subspace U, and we are claiming that this relation is equivalent. So first of all, you have to prove the reflexivity. That is, for all A belongs to V, A is related to itself. So if A is related to itself, what you need to prove in order to satisfy that A minus A should belongs to U, and A minus A is what? 0, 0 vector, and as U, capital U is a subspace, so it must need that additive identity, so 0 must be there in U. So A minus A, that is 0, belongs to U, so A is related to A in that way. Now if B is related to A, that is B minus A belongs to U. B minus A is a vector of your vector space U. Now what we know that this vector space is formed over which field? The field of real number R. So you can always pick up minus 1 from the field of real number R, and then you multiply minus 1 into B minus A, that will result A minus B, and as we know that the vector space is closed with respect to scalar multiplication, so minus 1 into B minus A, that is A minus B, also should be a member of your capital U, but that implies A is related to B. So basically from B is related to A, we can come to a conclusion that A is related to B. So this is known as symmetry, right? And the last one is transversity. What we can see that A is related to B, or sorry, B is related to A, so B minus A belongs to U, and say C is related to A, so C is related to A, so C minus A belongs to, okay, I can do it like what I am trying to say, the last part, that is in order to make it transitive, what is required that if these two must imply basically what we need to prove that if A minus B belongs to U and B minus C belongs to U, then it implies A minus C belongs to U, and that you can do easily. you just add these two vectors. They are vectors, they are element of the vector space capital U. So if you add them, the resultant should be another element of that vector space capital U. And what is that element? That is A minus C. So you are proving that this is, so you prove the transitivity. So that is, so here, so this is an equivalent relation, right? Now we have proved that this relation is equivalence. Now what we can write, that for a given space capital V, sorry, for a given space capital V, if we try to disregard, this is very important phrase I am using, disregard all the that generated by obtaining like what we are asking here, that for a given space V, capital V, what is, I am trying to explain it in my own way, that if we try to disregard the elements generated by like B minus A, that is an element generated by the obtaining the difference of two elements B and A belongs to V. Now all these difference belong to U, and we are disregarding all such elements, then what we'll get? Like, isn't it that we are trying to, like, an attempt of, you can say an attempt of identifying all the elements that are modulo U. So for all the A belongs to V, we can take our E plus U is is congruent modulo to U, and let us consider a space formed by the collection of all such plus u, right? Formed by all such. So let me use a different color, otherwise you will get confused. We are considering union of all sets of that A plus U. So this is called the quotient set of V modulo U, or some people call it V factor U, like they call it like just a minute, yes, V modulo U, or sometimes called this quotient set, quotient space. Few people call it factor space of V by U W, right? We denote it by so let us try to understand what it is. We are trying to discuss here that let us consider a set capital U such that or you can write it like right. Now if we pick up two distinct vector, when they will become congruent, they are congruent if U3 is equal to U3 dash. Basically you are talking about the plane, right? You have three dimension, you are like you can consider U1 and U2 are your x and y, and U3 is z, and you are fixing that z point, then like any two, the remaining coordinate will form what? A two-dimensional plane, typically a parallelogram. So any two parallelogram will be congruent to each other irrespective of their like values. So like the side length, they are congruent. So in other words, here that x3, or in terms of x, y, z, the z coordinate only matters. So if you try to think in that way, what you will get that V by U is basically of all such planes. Like you can consider a three-dimensional space as if you are stacking several two-dimensional plane on each other. Like those who are from electrical engineering background, they can visualize like we take very thin laminated means lamination, and then we piled up together to form a three-dimensional code. So you can it is in like that. Okay, and the last thing that we have to prove that how we can define it is a claim that this quotient space is just a minute. So, in order to make it a linear space, we have to define the two operations, that is the addition of the vectors. So, let us take two vectors and define their linear operation like and right, these are the definitions. So, what does this definition imply? That we will try to understand in a, like by taking that first example of parallel translation of line. Let us try to understand this. Here, just a minute. This is our U. Now let us have this is say A plus U. Just a minute. I think you can draw it using just a minute. So here I have completed the diagram. U is a unit vector of this subspace, and this A plus U, B plus U, A plus B plus U all are affine subspace of U. Now you can see here that this A plus U, it is a vector, and this line A plus capital U is a line passing through the tip of that vector A plus U and also A. So we are getting this line A plus capital U, this one, and then similarly we construct B plus U. Then the linear sum, it is the vector A plus B. You can easily find it out by obtaining, if you add these two vectors, then you will get this one A plus B, and similarly you can find out A plus B plus U. So you can understand that how the operation that we have defined is a linear one. For sake of understanding, I am considering this two-dimensional case. You can consider always abstract n-dimensional case. And if you want to realize identity for them, then it is also very easy. Like for A, you can always have that like A is the vector of V, so you can always have another vector minus A present there, so you will get a vector minus A, and that will give you some vector like minus A plus U, and you will get the line minus A plus U. So in that way you can always find out the additive identity of that, additive identity and additive inverse of that space. And similarly you can do or define it for scalar multiplication. And one last important point in this respect you should think about, we also talk about the dimension of this quotient space. We call it codimension U. We consider it codimension U is dimension V by U, and we can prove it later on. I will discuss more on this topic when we will consider it. It is like that dimension V is equal to dimension U plus codimension U. We can prove it, but that proof is not important. This result is very important for us, and if you are interested in knowing the proof, then I can also prove it for you. Okay, so these two lectures, the last one and this one, is not that much important, but from next lecture you will find we need these concepts will be required to understand the upcoming lectures, and that will be very, very important for the control system engineers, like that inner product space, Hilbert space, and then the Banach space, norm space. We need to know all this, and when we will study them, we need all this concept of this quotient space.